You're listening to With Electronics What's Up radio podcast, and each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronics specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. While they may not be the most glamorous or the prettiest components in electronics, X-capacitors play a vital role in ensuring the safety and the reliability of our devices. In today's episode, we'll be exploring the importance of X-capacitors in maintaining the stability of electronic devices across isolation boundaries. We'll discuss their construction, when and where to use them, and what factors to consider when selecting the right one for your application. We'll also explore the world of film capacitors, examining their different types, construction methods, and thermal specifications. We'll touch on electrical properties, degradation factors, and the strategic placement of X and Y capacitors. Plus, we'll be shedding some light on the limitations of regular X2 capacitors and the role of X capacitors in the mainline filter.
From the agenda, so I hope you have already all a cup of coffee and you can enjoy the session. So I have listed just the headlines, what I want to talk about. So coming from the types of film capacitors, also construction types, differences. Then some important things about the capacitor itself, like thermal specification, how is the electrical specification defined, what about the standards, which are present, and then important topics would be the degradation of capacitance. So as always, you have some aging effects in the products, and it's a difference if it's a brand new capacitor or is it a used capacitor. So I will show you some effects, and then of course what Cam also mentioned, like where we place X and Y capacitors, and also some restriction I want to talk about shortly. And of course, then in the end, I prepared an example of a mainline filter. I hope I can give you some insights or some thoughts, and how to select and build up the filter. Then, as I said, I start with the different types of capacitors. So of course, film capacitors is a wide range of products available. You can have a metal film as a base structure for the electrodes, or you could have a metallization, like you have a dielectric material and then you metallize your electrodes on it. And then it's also different if you use paper or plastic film, and therefore you will have in the end different coding, like so-called FP, for example, or MK. MK means then metallized and plastic as a base material. And I will talk about these three or these capacitors. Like we have a plastic film, mostly polypropylene, and we do a metallization on this kind of plastic film. So I will talk about MK capacitor, because also they are mostly used in the electronics. Of course, these other capacitors have their usage, especially also the military and so on, but this will not covered today. Then to give you at the beginning more insights about how the product looks. So we have our box type, so no teardrop products. We have boxed, or I will talk about box capacitor. And we have our winding element inside the box. The different layers are winded with a little bit margin on every side, that you don't have a short circuit. Then you have your contact layer, so a choke layer. So you spray some metal on the contacts or on the winded element. And then you have your pin, and then it's the fixed or the finished element, and you put it in a box and put some epoxy around to seal it. As I said, we have full metallization, so base material as dielectric, like the polypropylene, and then some metallization on it. And here you see in the picture, it's a single-sided metallization. Yeah, talking about the types. So as I said, there are different materials available. So mostly we use polypropylene. I have here in the tables a small legend. So polypropylene, we can say it's overall the best material, which when you think about costs, the different deviations about temperature, about dissipation factor, and so on. It's the best solution you can use for the mass production. So it's like a in the middle, I would say. Of course, then other material like PET are available, for example, for the cost and miniaturization. So it means that the minimum thickness of the film could be smaller compared to the polypropylene, and also the cost is excellent, means that it's not especially high. That it makes good for us to have a sale, but it's also a low cost product. But especially here for the temperature characteristic and dissipation factor, it's not as good as polypropylene. So it means the temperature, the operating temperature would be limited. Then for PEN, it's the same. So it's you have good characteristics for also heat resistance, but the stability of the capacitance over the whole operation range is not that good compared to polypropylene. And also for PPS, especially it's price sensitive, so it's really good performance, but overall when you build up then a mass product, because it's all related to the price, it's not so common to use this kind of base material. To give you a little more insight about it, just a few values, because to convince engineers, you present them some real values. I just highlighted here with red and green the maximum temperature here, and also water absorption. It's because of it will come later when we talk about the degradation. It's mostly water or humidity, which cause an degradation also. Here I highlight the water absorption rate. And important here, especially for the safety capacitor, is this the breakdown voltage with 400 volt per micrometer, and also self-healing properties. Because of this, they are mostly the polypropylene is mostly used also for the safety capacitors. Compared to PET, you have here a higher temperature range and then lower water absorption, but because it's not so stable with voltage, like breakdown voltage, and also the self-healing capability is not so high, it's not used for the safety capacitors. For the other two, when you compare the numbers, it's getting better. Especially, I think interesting is the higher temperature range, but because we need some impulse voltage capability of the product, we have some issue here with the breakdown voltage and the self-healing. This is why these kind of products, so when you have capacitor which use a different base film, you use it for a different kind of application or a purpose, like very stable tolerance or high working temperature, but not for the EMI filtering. Then when we come from the base material and now we build up our capacitor. So in the picture here, you see the construction in a schematic way. So it's like an paralleling of the different electrodes. When you parallel them, you get higher capacitance. Important, what I also said in the first or in the second slide, is like the choke layer, because this connects then the single electrodes, and then the connection here to make it solderable to the PCB. A cross section looks like this. So if you have your box, as I said, and you have the element and the different connection styles. So here it's just to bring a short picture about how it looks. And also when we go into an CT scan, that we say, okay, we use a computer tomography to see how a capacitor looks inside. On the left side here, a comparison between a good connection to the winding, and here a not so good connection to the winding, because here it's really pressed inside the winding, which means it could cause short circuits. So such things could be seen in a computer tomography way. And on the right side here, this is the choke layer. So actually these small balls, or yeah, maybe you interpret it in a different way, but for me it's like small balls, or small I don't know the English word, but let's say it's balls. And yeah, so you see here really the choke layer, and when you go with the device more into the winding, then you see here still a little bit choke layer, but here you see the single winding of the element. And so we can check about the product quality too, and we don't have to destroy the complete part. Then we use an aluminum zinc metallization for the AC capacitors. When you have pure DC capacitors, you use a different metallization. You can do it single or double-sided. The thickness of the metallization is around 550 nanometer, and yeah, you do some internal connection if you want to have different performance. So on the right side, you see some pictures about the different constructions. So the first you already see or saw. This is I would say the general one, or the mostly used one. Then you see here some different connections with your floating electrodes, and here on the bottom it's also double-sided metallization. And important is that when you have different requirements from your application, for example, you really need high DVT and high voltage, like you have high voltage rise time, then it could be good to look into double-sided capacitors, or the segmented one. It's really for high rel application. But the normal construction is the single-sided metallization. For the safety products, of course, especially the Y capacitors, because they have to fail as a fail open. They have then a special construction to ensure that in a failure mode that it's really open. Then coming to the base film. So there are different ways to cut, because you have to imagine that we have a so-called mother roll, where we have the complete film winded, and then we cut the different slices or the pieces, and then we use this to make then our real capacitor. And there you can have some kind of straight cut. And also what is really popular, I would say, is wave cut technology. So you have so when you have a wave cut, you see here you have a more connection surface, so you would have a better performance when you have high DV/DT products. Then there are also other possibilities, but not so common at them, or not so common in the market, especially not for the standard products for the X and Y caps. But I just, for the sake of completeness, I bring it here. Like TD means that it looks like a T and a D and a T, because it's like here you have some kind of T segment. So really this is like how the metallization looks on the polypropylene film, and you use different shape to ensure either the density, as the capacitance density, or the change of capacitance, also due to degradation, or to ensure voltage dissipation factor and so on. So this is always a trade-off of what is really needed also from the application side. Then the last thing for the construction is like you, I already told that you have with the choke layer, you connect the pins to the side, but what you see here on this slide here is like how the film or the metallization looks on this connection on where the choke layer comes. So it's called shape or the metallization shape. So you could have just a straight metallization, so everywhere is the same thickness. Then you could have some kind of heavy edge, also called heavy edge, that it's you reinforce this kind of area to have a better low resistance connection, that you bring in the energy into the winding. Or what is also common is a slope, what you see here, and this is really depending on the product. So for the X capacitors, for example, and Y capacitors, we use the heavy edge shape or the metallization, because we have these high DVDD, which could occur on the application, like an lighting event or a search event. So we use this kind of shape of the connection region. Yeah, coming from the construction side to the thermal specifications. So I will talk about mainly polypropylene and PET. So as you see, or when you remember what I said in the beginning, that these PET, the change, or that is not so stable over temperature. It also relates then that the operating temperature is limited here to 85 degrees. Polypropylene is up to 110 or 105. It's depending on, also on the manufacturer. And of course, the trend is that it goes to higher temperatures, 125, for example. Then an important point is, especially also for the in regards of the temperature, that you have to look into the data sheet about the derating, because depending on the operating point or where you want to operate a capacitor, you have to decrease the rated voltage. So there's a diagram or derating curve. You have to check them, or you have to check the diagram, or for example, what we have in the data sheet, we have the voltage described. It's a rated voltage up to 85 degree and the rated voltage up to 105 degree. It's different. Then you see directly what is the voltage could be applied to the maximum temperature. So please be aware that some parameters change. So the DC voltage I already explained. So dissipation factor will also change over temperature because of the dielectric material behavior, and also the capacitance change over temperature. To make this more clear, my colleagues in Berlin, they did some measurements. Here capacitance change over temperature and also dissipation factor change versus temperature, and there are a lot of graphs or lines inside, but we can summarize them in this blue box. They are all polypropylene based capacitors. So of course this is our match codes. They are, the first two are the safety capacitors, then we have general purpose, we have DC link, also polypropylene, and we have special safety capacitors for harsh environment, and also the Y capacitors, they are also using polypropylene. This is why we can assume it as this blue line. So the change of capacitance is not that big compared to the MKT, so like the PET polyester types. Here the capacitance change really a lot over temperature, and this is why the specification here is only up to the 85 degrees, because when you go higher, then the capacitance will change dramatically. For the Dissipation factor, you see some bump, I would say. This is because of the dielectric material behavior. So it comes from the material. And when you imagine that we measure at 25 degrees, so room temperature, you have not the biggest dissipation factor, but yeah, mostly the highest one for the polypropylene. And when you look at polyester here, yeah, there's also big change in the dissipation factor, and here also it's only valid up to 85 degree, because then it's also change here a lot in the higher temperatures. Yeah, coming from the thermal specification to the electrical specification, because this is important to know. As for example, for the capacitance measurement and the F measurements, this is also of course defined in a data sheet. Please be aware of the test condition, because when you use, as we do, an LCR meter and you use a different setup, then the capacitance value is different. The rated voltage, what I mentioned here, we say rated voltage here is 310 volt AC, and we have also a DC rating, 630 volt. This comes from the base material. So the DC voltage comes from the base material. What is the base material capable of to handle? And the AC voltage is defined in the IEC standard or UL standard. So the 638414. This is our working standard. Then, because it's also important, like the dVdt, so when this is too high in application, then the part could get damaged. And the dVdt is really defined through the base film, mostly about the whole construction, because of metallization, the size and so on plays a major role on it. And when you have fast voltage pulses, it really leads to the high currents in the capacitor, and this makes really a pressure on the contact area. And when this is too high, then of course there will be some breakthroughs, or some where's the weak point, it gets more and more destroyed. And well, this is why we have to take care about these value also in the data sheet. Yeah, going a little bit more into the specification. So there are also more graphs available where you should have a look at it, like the VRMS versus frequency and the ERMS versus frequency, so the current graphs. They really correlate with each other, because there are some factors or some limitation, and these are in the beginning. The voltage is limited to corona discharges. It means that also so-called partial discharge. So it's checked on which value you could continuously apply an AC voltage here, and there is no partial discharge, because when you increase the rated voltage, also the partial discharge inside the capacitor will rises. Then here we have the limitation in this area due to self-heating. So when you apply the maximum current, the product will self-heat. Will heat up itself. For example, for our products, it's 7 degree or 10 degree or 10 Kelvin. And the last thing is the limitations to the contacts. It means that it really depends how you connect the part to the how the pins are connected to the product, and also to the PCB, what kind of currents and voltages regards to the frequency you can apply. These graphs are not available in a data sheet. Mostly it's available through different tools. For us, it's accessible through our Red Expert online tool. Then, we provide also a lot of data for selection purposes, like the impedance, what you see, like the capacitance change over temperature, dissipation factor, and also capacitance change over frequency. But the most critical thing to measure is the ESR, because it's so low that yeah, you see here also in the beginning that it's the measurement setup and the measurement device has problem to measure it. But yeah, we found a way, or we have test set up that we can measure it, and we can also provide it on request. So here you see the real measurement, and then you can also imagine that, of course, higher the frequency, because of self-heating, less current is capable or allowed. When we talk about the standard, so yeah, there's a lot of standards listed. You don't have to read everything. The most important one for me especially is this IEC 6384-14, as I said. It's the definition for the safety capacitors for electromagnetic interference suppression connected to the mains. In here, or in this standard, there are a lot of definitions what the products has to be, yeah, how to say, capable of. And of course, we have to test everything, and it's covered by UL and VDE, that they also check that everything is passed. And the other standards, I listed it because of the sake of completeness, because there are also standards which describe metallized polypropylene film dielectric for AC and DC pulses. Or there's something missing, sorry. But also with metal foil oil DC capacitor. So this really a big portfolio of standards, but the most important one I marked here. The equipment you see on the right side, I will now go through it. So these are the equipment we need for the reliability testing for the product. And one thing is we have to do the impulse voltage test. So as you know, for example, X-capacitors, X2 capacitors has to withstand the 2.5 kilovolt impulses. The Y capacitors, Y2 has to pass the 5 kilovolt impulses. And this is a destructive test. So we really, in worst case scenario, we really destroy the part, because when we play, because we want to know the limits of the product, and we go higher than specified, the part will be break, and there's some parts get cracked and so on. And for the base material here is really important, what I said also in the beginning in the table, that you have some kind of voltage definition per microvolt, so the breakdown voltage. And when you assume we have a 7 micrometer base film, what is quite typical, we have around, when you just imagine the base film, we have 2800 volt breakdown voltage. And this is what then we test with this device. We apply 2.5, because this is defined by the norm, and see how the capacitor reacts. And we check here mostly the self-healing capability. It means there could be some breakdowns, what you see here. So when we apply here the voltage, and then when there is a breakdown, also when there's some impurity or an part or an area which is has some issue, then we have a breakdown, the capacitor heal itself, and then the next impulse come, and then maybe everything is good. But in here you see how some breakdown looks like in the testing. Yeah, just to make it more clear or in picture how this breakdown will occur. So here the gray is our dielectric material, then we have our metallization, and imagine here is a breakdown point, some impurity or some failure in the metallization. When there comes an impulse, then this is a short circuit. Then there's a concentration of the current. So there is the hotspot. So there will be a lot of heat and respectively current. And then this area will vaporize or gets vaporized. It means that the metallization will be vaporized. So it really goes into the surrounding. And but then it's healed. So then there's no short circuit anymore, and the capacitor functions as normal. The second thing what we test with a quite huge device with a big tank capacitor is the so-called active flammability test. So we place our specimen here and we wrap them with cheesecloth, and we check when there is an failure. So we apply a rated voltage. So you see here, this is the 230 volt AC voltage. And then we apply the 2.5 kilovolt impulses. And when there is some breakdown and maybe some arc, then these cheesecloth get burned. In the worst case scenario, it really takes fire, so it really ignites. Then of course test is not passed, of course. But this is something we have to check for the capacitor, and regularly also to get the certification. So these are the most important tests for the safety features of these products. Then what I said in the beginning also, that we have some kind of capacitance drop. We did some measurements in our lab. You see here the oven and the measurement equipment. This is a quite old setup. At the moment we do it differently, but just to see also some kind of how we do it. So we have a source, and then we measure the capacitance. Here it's not that big, I would say. So we measured around 1,000 hours. Start at around 468 nanofarad, and in the first time, so when we apply here 60 degree and 230 volt, so no humidity, just voltage and temperature, we see that there is some drop, and after 1,000 hours you have around 460. So it seems not that much, but it's also that the operating condition is not really critical. So 60 degree, I would say, is not that critical operating condition, and also no humidity, so it's quite optimal, I would say. But of course there are some capacitance drop over time. When you have high voltage or over voltages, then the capacitance can drop due to partial discharge. What I said, that there's also some breakdown between the layers, and it will reduce metallization surface, and so the capacitance. Then the high temperature will shrink the edges of the film. When the temperatures are too high, then you will lose the connection to the outer layer, to the connection. So you will have some drop of capacitance. And when you have some humidity around the capacitor, then it can go inside the capacitors to do diffundation, and then you will have some corrosion, and the metallization layer will peel off because you have air inside. So you have a winded element, you will have some air inside. When then moisture comes, then moisture, air, metal will corrode. So the mechanisms are called, as I said, partial discharge. We have electrochemical corrosion, self-healing. This is because of what I said, of the over voltages, and also we have oxidation, which reduce the metal film. And just for you to see how such a film looks like, so here you see less metallization area. So the I would say the black one here is the metal, and you see here there's some metallization gone away. Sometimes you see also some breakthroughs, but this is not so easy to detect. And also here, especially this electrochemical corrosion can occur also only in a small region. So it really depends on how the product is used, and what kind of operating conditions you have around the capacitor. There was some changes or some thinking also in the standardization committee, because there are capacitors available which are used for the harsh environment or for high humidity and high temperature conditions. They have, the good thing is they have stable electric characteristics, and they are also now described in the new standard. So there's a new edition. I think the 5th one is the newest one. There's the annex, which describes these special temperature humidity bias grades, as a THB, so-called. And it goes up to grade 3 test B, or test to condition B, which means you test them at 1000 hours, 85 degree, 85% humidity with rated voltage, and then the capacitance should not drop more than 10%. So this is roughly summarized what is described also in the standard. Just to see or to show how it looks in the data sheet. This is this humidity robustness test, and we also do the testing here. And for me, really interesting was when I looked up what does it really means for the humidity. How many water is inside such a chamber then? So when we look at 40 degrees and 95% of humidity, so this is the so-called damp heat test. So it's like also so-called category definition. You have around 50 gram per cubic meter. When you have then these higher conditions like 85, you have around 300 gram per cubic meter. So there's a lot of water inside and a lot of water which can go inside the capacitor. When we compare it, like the standard capacitor X2 and also to the THB capacitor, they have low moisture absorption, and what I said also, they have good lifetime. It means that you have not that high capacitance drop, but they are, because of construction, they are bigger than the regular X2 capacitors. To give you an roughly idea how this degradation takes place. So when we measure it before the test and after the test, here you have roughly this 10% of drop. It really depends. It's sometimes better, but the limit is the 10%. But regular X capacitor, it does not really matter from which vendor or which manufacturer you will get it. When you do these tests, you will have a capacitance drop, and you have here it's around, I don't know, maybe a drop of 30 or 40%, but this is just as typical. So it's not an absolute value here. It's just that to show you that there is a change, and you have to be aware of it when you have these harsh conditions. Because I'm also proud of our lab in Berlin, what we can do, just to show you how we do it in Berlin, the measurements. So we have our chamber here. My colleague Jon, he designed an own multiplex application or circuit that we can measure all the specimen we have inside. So they get switched. And we don't have to put it out and measure it one by hand. So this is some kind of nice automation how we measure it. So we can also then measure a lot of products. And now we are coming to the thing what Cam also mentioned in the invitation. So about the use of X and Y capacitors and where you place them. So these capacitors you place across the line between L and N, and it protects the application from the interference from both sides, so from the AC or from the mains or from the application, and also it protects in a limited way the surge voltage also coming from the AC. The Y capacitors, as you see here, they are connected between each line to the chassis, in the chassis. It filter out common mode noise. The X capacitors doing the differential mode noise. It's designed to fail open. This is really important, but we have some limitation about the leakage current. So this is why sometimes you are not allowed to use Y capacitor because of the leakage current, and this you have to check with your standard or about the definition from the application what is allowed and not. The voltage classes, I already did a sneak preview. They are defined also in the standard, and they depending on the classes. So X1, you have to have a 4 kV impulse. Y1, for example, 8 kV. So it really every time it gets doubled, and this is what a requirement we have to fulfill to produce then the capacitor that are also then rated for these kind of classes. If we have the product right, or if we do our job right, we get then also the approval. So we get a certificate, and for the certificate, you could have maybe NEC 10, then it's called a VDE, or NEC 15, then it's the UL. So there are different houses or different companies who do this kind of testing. Of course, we have for some we have the VDE because it's a European certificate. Then we have the different UL and CURS certificates for the different market. Also the CQC for the Chinese market are available. And one interesting thing is that when you talk about ceramic capacitors, so for example, we have also ceramic Y and X capacitors. This certification is done by TÜV or UL. So you don't get, of course, you cannot print the VDE logo on these kind of products. It's not possible. But this is mainly covered by this organization to prove if the product is the right one. Then one restriction I want to talk about shortly is that you have to take care that the Y cap or the X capacitors, they are most of them are designed to be used in parallel to the application, so like parallel to the mains, and not approved in this kind of series application, like it's called a capacitive power supply or a capacitive dropper. And this is then all mentioned in the data sheet. There's also some change in the data sheet for us. I just want to make you aware of it, that we also replace the clearly application, so where you can use it here across the mains for the normal film X2 capacitors. And then we have this kind of special series, what I mentioned is THB, which has better enclosure and better performance also about harsh environment. Some of them are for both, so across and in series, but please really check the data sheet because not all of them are allowed for both application. That just as a short talk about the restriction of capacitor. When we talk about the mainline filter, so I put here a picture of it, how it could look, mainline filter. So this is with a discrete construction. Of course you have your fuse holder, because when you're working with a varistor, you used to have a fuse, because when this gets in short, then something has to make open the circuit. We have our X capacitors, we have our discharge resistor, which is important because the X capacitors has to be discharged really short. We have our common mode choke, because we need them to have the attenuation for the common mode. Then we have our Y capacitors, and important thing also the grounding, to have a good performance of the Y capacitors, especially when you do not ground them, then of course you have no effect. So the X capacitors, they make the attenuation in combination with the stray inductance of the common mode choke. So you see here that it's from the stray inductance and combination with the X, also with the capacitance value, and the Y capacitors, they use the inductance value in combination with the capacitance value to create then the common mode attenuation. Yeah, here you see the schematic of such an mains filter. It's a little bit different, especially the placement of the Y capacitors, and this is also what I want to make you aware of that the best placement of the Y capacitors would be here after the common mode choke, in direction of the device here in, for example, the switch mode power supplies, to have a good performance of the whole application. Why this is so, I try to make it more clear. So when here's the common mode choke from the picture before, and then we have the Y capacitor. Here's the protected earth. Here would be our switch mode power supply. Here would be a flyback design, and we have some parasitive capacitive coupling due to the connection here to the chassis and so on, and we have to keep the return current path as compact as possible, and here the current can flow then directly back, and it's also because of the high impedance, the current source and the listen, which is typically 5 ohm. So please, when you design it by yourself, please take this into account, that it would be the best placement. For the Y capacitors, what I said, we have also some kind of leakage current here for one phase system. The largest leakage current would occur for the grid voltage of 10%, also when you have the maximum plus tolerance and frequency 60 Hertz, and our tolerance of the capacitance value in the positive. To calculate it, you can use this formula from the grid voltage, the 2PF for the filter, and the capacitors here. And of course, I did the calculation for the example when we use 1 microfarad and 5.6 nanofarad as a Y capacitor, we get around 0.9 milliamp. And now this is the thing you have to check with your standard or with your requirements, if this fits to your need. If it's too high, of course, you could try to decrease the capacitance values, but then of course the EMI performance will change. So this is the trade-off. You have to get the best setup. Then for the discharge resistor, so the voltage after power plug removed have to be 60 volt in less than 1 second. So this is defined by the standards. There are some calculations what you can do. I described the calculations here to sake of completeness, but there are also some nice tools like here from DigiKey to calculate a discharge resistor. And please take in mind or take into account the power rating, because when it's really dissipate power, and it doesn't have to burn away when it's the device plugged off the mainline. And also important is the creepage and clearance. It really depends what kind of requirements you have, that you selected the right size of the resistor. For our sample here, we calculated a 222 kilo ohm. We choose 220 kilo ohm because this is the next nearest one, and we have a dissipation of around 270 milliwatt. So we have to check the performance of the resistors to select the right one. Most most of the time you use an THT type because X capacitors, Y capacitors are also THT. But there are also ICs available on the market from power integration that make this discharge of the capacitor really fast, or in the zero in the zero phase. And it's also there then these kind of ICs to have a good standby current, for example. So going now to a complete complete example, when we calculate a one-stage filter, when we want to have a common mode differential mode damping 40 dB for 300 kilohertz, it means the corner frequency would be 30 kilohertz. So of course, first thing, we have a kind of LC filter, 40 dB per decade. Then the corner frequency, 30 kilohertz. It means that it's a one tenth of the switching frequency. What I said here, 300 kilohertz, and there we want to have the damping. Then we define the Y caps. It's like in this example we do it like from a rule of thumb or from a stomach, that we say 4.7 is a good value. So we have the total of 9.4 as a Y capacitor. Then we define the common mode inductance, what we need for the 30 kilohertz, what we want to damp. So we have here the normal equations to calculate the inductance. So we get 3 millihenry, and we choose the nearest one. Here is 3.3 millihenry. Then we do the cross check that everything is right with the 3.3 millihenry, and we still have our 41 dB what we want to have. So everything's fine here. Then we calculate the differential mode inductance. Therefore, we need the XL, so the inductive, the blind inductive value from the common mode choke. We can use Red Expert or online tool or the impedance curve to get our value. So here we have around 15 microhenry as a stray inductance for this kind of product. And with this stray inductance, we can calculate the X capacitor value because we know our corner frequency, we know the impedance. So we have the 2.2 microfarad as X capacitor. So we have then finally the value. And we also do a cross check with the 2.2 because calculated is 1.9. Still, we have enough attenuation. So with the chosen product, everything is good. Then when you design your PCB, your mainline filter, I would recommend, or we recommend you that at least you have a 3 millimeter air and creepage distance between the conductors, especially when you have 250 volt AC, and 8 millimeters to the PE, to the protected ground. And please take also into account the contamination, so the pollution degree, to check your distances. For the capacitor, of course, it has to be at least X2 and Y2. And what always helps is that when you dimension the component, that you use the maximum values, including tolerance, that you have everything take into account. And for the range or for the placement, it should be very low inductance, especially for the Y capacitors, because as lower the inductance, the better performance you have. And when you have to place more, when you have maybe two-stage filter with two common mode chokes, then please check how you place them, because they can also influence themselves. So one hint would be that you increase the distance when you have the possibilities, or at least you rotate the product by 90 degrees.
So Frank, when you're mounting those Y caps, what do they look like? Because you showed examples that were through holes. So do you guys have a line of parts that are also surface mount, or what's going on down there?
Yes. Yeah, so this is one special thing for us, because we have only SMD Y capacitors at the moment. So we are working to bring also THD Y capacitors. But yeah, this is why the examples here is with the SMD types. You're right. These are difference here for my example. Yeah, and then at the end of my presentation, yeah, just we have this also available for you if you have to design your own mainline filter. Then when you need to play, so I would say, of course, you do engineering, but when you have to select different values and so on, with this kind of boards, you can yeah, you can select different parts, you can test it and see what is the best performance of the products.
You may also be interested in our lineup of film and interference suppression capacitors, as well as our free component selector and simulator Red Expert, which includes the capacitor selection tool. Find it all online at www.we-online.com/redexpert. In addition to the capacitors, the Worth Electronic range also includes EMC filters, components for ESD over voltage protection, transformers, connectors, and so much more. You can find the entire lineup of resistors, capacitors, and related components available at Worth Electronic online. And for any questions, click the icon to talk to our live chat team. To view the materials and replay the video, check out our YouTube page. You're listening to Worth Electronics What's Up Radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.